Hello everyone. In the previous lecture, we were looking into how electrical resistivity survey can be carried out in the field. There are three major ways by which we can carry out the electrical resistivity survey. What are they? One is electrical profiling. We had elaborately looked into how electrical profiling can be carried out. Electrical profiling is carried out mainly to understand the lateral variation in the lithological formations. The second method is vertical electrical sounding. That is what we had seen in the previous lecture. Toward the end of the last lecture, we had seen this slide. That means, how do we understand about the subsurface? So, what do? We plot electrode spacing versus apparent resistivity. Whatever is the method which you use. If you use Venner method, we plot electrode spacing is nothing but A. If we use Schlumberger method, electrode spacing is nothing but AB by 2. If we use dipole, the electrode spacing is nothing but N. So, electrode spacing versus apparent resistivity we are drawing. The shape of the curve help us to understand about the subsurface layers. This is what we had seen in the previous lecture. So, today we will continue with the same. How can we interpret the data which we acquire by electrical sounding methods, which is nothing but vertical electrical sounding methods. What are all the different methods of interpretation? These are some of the methods of interpretation. First is methods of asymptotes, curve plotting, cumulative curve plotting, S-type method, curve matching method, partial matching method, use of software. These are all the methods which we are going to see. Actually, what we are trying to carry out from vertical electrical sounding is, during the field survey, we conducted the sounding by keeping the center point of the spread constant, and we progressively moved the electrode on either side, as I have drawn here, which means we have acquired a data of electrode spacing versus rho A. So, this data of electrode spacing and rho A can be plotted like this. This is electrode spacing, this is apparent resistivity. So, we end up in getting a relationship as shown in this diagram. So, how can we interpret this curve? This curve is known as resistivity curve. So, these are all the methods of interpretation. We will see one by one. First is method of asymptotes. Here what we look for is, as usual, we plot depth versus apparent resistivity. As a convention, we plot electrode spacing in log scale as well as apparent resistivity in log scale if we carry out the method in Schlumberger. If it is Venner method, we plot normal versus apparent resistivity in log scale. Why we are taking up such sheets, sometimes log, sometimes semi-log. So, conventionally, the type curves for Schlumberger is available in log scale. That is why we plot like that. We are going to see little later. So, now let us have a look at this resistivity curve obtained by Schlumberger method. We are plotting AB by 2 versus apparent resistivity, right. These points, all these dots are the data we have obtained during the field investigation. That means, how do we carry out the field investigation, right. This is the center point of the spread, this is M and N electrode, these are A and B. A and B electrodes are progressively moved on either side, so that the depth of penetration keeps increasing below the surface of the earth. And then for corresponding arrangement, we measure the value of apparent resistivity. So, we got the data of AB by 2 versus apparent resistivity. So, this is the data we have obtained during the field work. So, we are plotting AB by 2 versus rho A as seen in this diagram. So, here what we look for is, we look for inflection points. What do we mean by inflection point? Inflection points are the points where there is a major break in the slope of the curve. So, here I see there is a break in the slope of this curve where I am marking a red cross, right. Over there I feel there is a major change in the slope of the resistivity curve. So, what does the major change in the slope of the curve indicate? It is indicating the presence of discontinuity below the surface of the earth, right, which means at this depth there is a change in the rock type, right. This is the vertical direction, somewhere here is the lithological contact. This is layer 1, this is layer 2. So, this contact is at this depth of 200 or 300 meters. So, this is how we carry out interpretation by this method. This method is the simplest. So, what we are doing here is, we are drawing the resistivity curve. By visually looking at the resistivity curve, we try to bring out the points at which there is a major change in the slope, right. These points are indicated on the graph itself. They are nothing but inflection points. Corresponding value at the x axis indicate the approximate location of the contact plane. So, this is the simplest method of interpretation of electrical resistivity data. Then the second method is to plot the curve like the previous method, and also we are able to estimate the what is known as additional coefficient known as reflection coefficient. So, what is reflection coefficient? Reflection coefficient K is indicated by rho 2 minus rho 1 divided by rho 2 plus rho 1, right. So, what are rho 1 and rho 2? They are nothing but the resistivity of the first layer, resistivity of the second layer. How are we able to arrive at the resistivity of the first layer and second layer? So, we are able to arrive at the resistivity from all these points, right. So, here I have marked this point as the inflection point. That means that is the point where there is a change in the type of the rocks, right. There is a lithological contact. This is the ground surface. At this depth, the rock type or the lithological formation changes. That is why I see a major change in the slope of the line. This is my interpretation, right. So, I take the average of this numbers, right, this apparent resistivity average, which is approximately 100. For all these resistivity values, average is around 600. So, layer 1 is of resistivity 100, layer 2 is of resistivity 600 ohm meter. So, using this relationship, we are able to determine what is known as reflection coefficient. So, in this method, we are able to determine the reflection coefficient, and using that we can also determine the resistivity of the top layer. So, what is the additional information which we get here? We are able to get the value of reflection coefficient, and also we are able to locate the contact plane, right, with from the x axis. This is the x axis. So, this is the point of inflection. So, this is the location of the contact plane. So, wherein there is a major change in the curve. There can be one more also, right. So, this is also done by visually interpreting the resistivity curve. This is the second method of interpretation. Then the third is popularly known as inverse slope method. Here what we are going to do is, we have a data of AB by 2 versus rho A. If we are doing Venner method, if it is a Schlumberger method, if we are using Venner method, then what is the information we have? A versus rho A. Whatever is the method which we follow, we are going to also calculate what is known as cumulative resistivity, apparent resistivity, right. Suppose if the resistivity is 0.1 here, 0.02, here it is 0.13. So, what is the cumulative resistivity? 0.1, 0.12, 0.25. So, this is how we note down the cumulative resistivity. Then in this method, we are going to plot AB by 2 versus cumulative resistivity. That means previously we were using the actual apparent resistivity. In this method, we are going to make use of cumulative apparent resistivity. What is the advantage of using cumulative apparent resistivity? We end up in having a plot of cumulative apparent resistivity versus electrode spacing. So, the values will obviously increase because it is a cumulative value. Second value or third value will be always higher than the previous value, isn't it? So, you will end up in points plotted which will continuously the values will increase. The advantage of cumulative resistivity plot is the points will more or less fall on a straight line. So, all points falling on a straight line are connected, as you see in this diagram. Here are other set of points which are also connected. Here are the next set of points which are also connected. So, we end up in having several segments of straight line in the cumulative curve plotting method. Hence, our job of interpreting this diagram is little bit easy compared to the resistivity curve which we had seen on the previous slide, right. So, here since we have got different segments of straight lines, the number of straight lines indicate there were so many layers present below the surface of the earth, which means beneath the surface of the earth, in this case there were 4 layers. This is the ground surface, this is layer 1, 2, 3, fourth one is of infinite, we do not know its thickness, right. So, this is how we are able to interpret the cumulative curve, right. And what are the thicknesses? So, this is the change in the break in slope. So, this is the thickness of the first layer. This is the thickness or depth to the second interface, that is, this is the depth to the first interface, right, and this refers to depth to the second interface. This refers to depth to the third interface. Okay. So, this is how we are able to determine the depth of the interfaces, and average of all these resistivities give us the resistivity of the first layer, second layer, third layer and so on. Okay. So, this is how we are able to make use of cumulative curve plotting method to understand the subsurface. Then the next is S-line method. In S-line method, we are trying to understand the effect of total longitudinal conductance. Hope you can recollect few lectures before we had seen the analogy between the electrical resistivity as well as the water conductance through the formations, right. So, making use of the similarity, we have another method of interpretation which is known as S-line method, which is nothing but the ratio of different layers to their respective resistivities, right, and the ratio of different layer to their resistivities is known as conductance, right, known as conductance. So, the total conductance is determined from slope of the terminal branch, that means the end of the curve, right, that too which is rising at an angle of 45 degrees. That is what we call it as S-line method, right. This method was suggested, or subsequently the person who was suggested is, they have come out with a research paper in which they try to relate how transverse resistance is related to longitudinal conductance of groundwater. So, this is the transverse resistance of electrical flow that is related to longitudinal conductance of groundwater flow beneath the surface of the earth. Right. So, here we as I had shown you on the previous slide, S is numerically equivalent to the inverse of slope of this line. So, inverse of slope of this line, right. So, this is determined by the intercept of extension of the resistivity curve, right, approximately at 45 degrees. So, extension of the resistivity curve so as to meet the horizontal axis. So, this is what is known as the S type method or inverse S method, right. In this method, we try to understand what is the approximate value of S by extrapolating this S line. So, this is known as S line method. So, as the increases in the value of S from one sounding station, from one station to the other station, indicate the increase in the total thickness, right, total thickness of the layer, or decrease in the longitudinal resistivity, or both, right. So, as the value of S increases from one station to the other station, it indicates, for example, we have conducted vertical electrical sounding at all these stations, station 1, 2, 3, 4, this is station 4, this is station 1, everywhere we have done vertical electrical sounding. Imagine from left to right, the value of S we are getting from the S line method is if it increases, that indicates probably beneath the surface of the earth, thicknesses of the layers are increasing. So, this method of interpretation is known as S line method. Then the next method of interpretation is known as curve matching method, right. So, in curve matching method, we have prepared theoretically plotted master curves, right. So, curve obtained by us during the field work is matched with the master curves. So, what is the relation we have got until now, right? Whenever we do vertical electrical sounding, we end up in having a relation between spacing, that is electrode spacing versus rho A, right. We have this plot, or how did we get this plot? By carrying out the field work, right. Now, we have this plot of values, and we also have what is known as theoretical master curves. How did we arrive at theoretical master curves? We have assumed, that means especially this researcher Schlumberger has assumed different configurations of subsurface, right. This is layer 1, layer 2, layer 3. Imagine layer 1 is of 1 meter thickness, layer 2 is 1.2 meter thickness, right. Then resistivity values, true resistivity of layer 1, 0.01 ohm meter, this is 1.302 ohm meter. Third layer is 4.132. I am just writing some number, right. Mainly to explain to you how did we prepare theoretical master curves, how we have arrived. So, as I have drawn here, this is the ground surface. We assumed layers of different thicknesses and corresponding resistivities, right. For such a imaginary subsurface conditions, if you carry out vertical electrical sounding at the surface, right. If you keep increasing the electrode spacing, as I am showing here, this is the distance between A and B electrodes. So, A and B electrodes are progressively increased over this imaginary hypothetical earth. What will be the resistivity value, or apparent resistivity value, which we are going to get, can be theoretically computed, calculated, right. So, for this 1, 2, 3 layers of different thicknesses and different resistivities, we can theoretically arrive at the resistivity curve. That resistivity curve is known as master curves. So, this researchers, especially Schlumberger, has assumed different combinations of layers. That means, here we have assumed 1 meter thickness, 1.2 meter thickness, that is the second layer. For different thicknesses and for different apparent true resistivities of layers, theoretically he has plotted the master curves. Is it clear? Right? That means, we assumed layers of different thicknesses, different true resistivities over such a assumed earth surface. If you conduct vertical electrical sounding, what is the expected apparent resistivity values has been theoretically calculated. Using these theoretical calculations, master curves are prepared. As you see in this diagram, this is one set of master curve. Now, we have the field data here, right. Here is the field data. I superimpose the field data over this curve and try to get the best matched position. Suppose if this field curve, this is the curve which we have obtained by plotting the data we have got from the electrical resistivity survey. This white sheet is the theoretical master curves. Now, we superimpose the field curve over the theoretical master curves and try to get the best matched position. We need to keep the axis of both the sheets parallel to each other. We should not rotate the sheet, but we should keep their axis parallel and try to superimpose one over the other and try to get the best matched position. Suppose if both the theoretical curve and the field curve are matching to certain extent, what can we arrive from this? So, we can decide that whatever was assumed to prepare that particular theoretical curve is likely to exist at the site where we carried out our investigation, isn't it? Because theoretical curves were assumed theoretical curves were prepared by assuming different configurations of subsurface. One such theoretical curve is matching with our field curve. What does it indicate? So, whatever we have assumed to prepare the theoretical curve is likely to exist at the site where we carried out the electrical resistivity sounding. So, this is how interpretation is done by curve matching method. So, several curves are prepared and this data is available both as hard copy as well as the soft copy. So, our data is superimposed over that manually in curve matching method. Once if you identify the best matched theoretical curve, whatever we have assumed for the theoretical curve is likely to exist at the site where we carried out the resistivity sounding. This method is known as curve matching method. Then this is what I have shown you in the previous slide. So, here we have the both field curve as well as the theoretical curves were superimposed over each other and we try to get the best matched position. So, this dotted line is the field curve and all the solid lines are the theoretical curves. How did we arrive theoretical curves? Each theoretical curve were derived by assuming certain configurations of subsurface. This is layer 1, layer 2, layer 3. Obviously, all these layers were assumed to be homogeneous and they are of uniform thickness. Over such a site, if you carry out Schlumberger survey, what is the apparent resistivity value which you are expected to get? Using that, all these black lines were drawn, right. At the field, we carried out the resistivity survey and we have drawn the resistivity curve based on the data collected from the field, that is this dotted line. So, this dotted line, the field curve is usually plotted on a transparent sheet and this transparent field curve is kept over the master curves and we move the transparent sheet either right or you can move anywhere, but always axis of both the sheet at the bottom, this axis and this axis has to be parallel, right. Now, we got the best matched position. For the best, from the best matched position, we can determine, right, the thicknesses of layers, not only thicknesses of layers and whatever is the resistivity we have assumed, right, that is also likely to be the same for the site where we conducted the resistivity survey. Okay. So, this is what is the curve plotting method. The same is today also possible by known as partial curve matching, right. Why we need to go in for partial curve matching? So, when we assumed and prepared theoretical curves, it is really difficult to assume more than 3 layers because the computations are done manually those days, right. So, what is available as master curve today is for the combinations of 3 layers. Beyond that, it is also mathematically difficult to arrive at what will be the apparent resistivity which we are expected to get at the surface of the earth. So, we have master curves prepared only for 3 layer case. Suppose the site where you are conducting the survey has got more than 3 layers, right. So, there are, let us imagine 5 or 6 layers are present. Then what we do in partial curve matching is the curve which we have obtained can be split into 2 or 3 more parts and each part is comprising of only 3 layers. So, we can go to the previous method we have seen, that means 3 segments of lines can be matched with the 3 layer case and then we can shift the curve to the newer location as if that is the origin of the resistivity curve, right. So, you will be able to determine the thickness of the subsequent layers. That means, if this is the field curve which I have got, right, these are the layers, right. I mark this 1, 2, 3, 4th layer, then this is 5th layer, 6 layers are there, but our type curves are only for 3 layers. So, what I do, I can take only this part of the curve and match it with the theoretical curve and determine the thicknesses of layer 1, layer 2, layer 3. Then I match only this part 3, 4 and 5. Okay, then I mark only 3, 4 and 5 part. After completing this, I take 4, 5 and 6. So, this method of matching is known as partial curve matching method. Then what is the next? Next is, as I was telling you, the master curves or the theoretically derived values are also nowadays available as a database, not nowadays in the sense last 20-25 years, this database is also available. So, several commercial developers, right, have come out with some software which has got the data in that. So, this commercially available resistivity interpretation software can automatically do the job of curve matching, right. That is one example I am showing here. For a site near Chennai, we carried out a resistivity survey. All these block dots are the resistivity values which we have obtained during our field investigation, right. So, what we need to do? We need to give this data as a input to this software, that is the data of AB by 2 versus rho A apparent resistivity, that is what is this black dots. The system, the software will automatically try to find the best matched theoretical curves that is available in the database. In this case, you see two such best options, right. One is shown in red color, another one is in green color. So, this is option 1, option 2, because system itself is finding it difficult to choose which is the best. So, it leaves the choice to us. So, it is a supervisory matching. We need to now decide whether we are going to go ahead with 1 or 2. The moment you choose, automatically the thicknesses of layers as well as their corresponding true resistivities are. Now, imagine we have chosen 1, this is for the chosen red color 1. How do we make sure whether the model we have chosen, that is 1, is correct? In order to verify that only, we need to do some field investigation too. Maybe we have to do drilling at a particular site, at this site, and check whether model 1 we have chosen, the curve number 1 we have chosen is right. Whereas, if drilling at the site indicates if 1 is not correct, 2 is much closer, then we need to decide to choose 2. Okay, that is why in sounding method, suppose if you do 30 or 40 vertical electrical sounding at the site, at least 2 or 3 boreholes are necessary to see whether the way in which we are interpreting the data is correct or not. If not correct, we need to refine our method of interpretation. So, these are all the different methods of interpretation of vertical electrical resistivity data. So, in this lecture, what we had seen today is what is vertical electrical resistivity sounding and what is the data which we get out of vertical electrical sounding. The resistivity curve which we have obtained from the vertical electrical sounding can be interpreted in number of methods. These methods we had gone through. Toward the end, we have seen this particular method. In this method, the interpretation is done automatically using the commercially available software. In the next class, we will continue to look into some more details on the electrical resistivity methods. Thank you.